welcome to the second of these joint events that we've been doing, brought to you by the committees of AIG, led by Bill Reid, GSA, led by Anne-Marie Toscolini, and WMESA, which I understand Fernanda is the lead of that, but she's not able to be with us. I think she's interstate. So Maddie is here representing WMESA this evening. My name's Mark McLean. I am the president of the Victoria branch for ASCG. Excellent. So it gives me great pleasure to introduce Professor Peter Betts. I'm going to embarrass him a little bit. Pete was actually my master supervisor almost 25 years ago, I think it was now. So not to try and make you feel old or anything, Pete. Peter has a very long list of impressive achievements, and his bio, which I will read to you, only scratches the surface of those. Professor Peter Betts is a geoscientist at Monash University, serving as the Deputy Dean of Engagement and Graduate Research within the Faculty of Science. He's a Professor of Tectonics and Structural Geophysics at the School of Earth, Atmosphere and Environment. His research expertise encompasses structural geology, aeromagnetic and gravity geophysics, with a focus on the geological synthesis of the Australian continent, Precambrian plate tectonics, and neotectonics at convergent and divergent plate margins. Throughout his career, Professor Betts has contributed to over 130 research publications and authored over 35 technical reports for governments and exploration companies. His work has significantly advanced the understanding of the evolution of the Australian plate, continental rift evolution, microcontinent tectonics, subduction dynamics, and the application of geophysical methods in structural geology. Probably not too many people outside this room would understand what that means. His most recent paper is a review of geological signals in aeromagnetic data, which will be the focus of his presentation today. Please welcome Pete.
Thanks, mate. So interestingly, I've got my Mark is my first master's student, and Helen Williams is up there in the background, and she was my second PhD student, but my first geophysics PhD student, also from about 21 years ago. I think we joined, and she's just recently moved back to Melbourne. So I just want to acknowledge Helen, but also a plethora of other PhD students that I've had over my journey. There's about 30 of them, and about 70% of them have had some component of geophysics in their project. Sometimes a small amount, often the entire project was geophysics. I don't see myself as a geophysicist, and Ashbourne over there, neither would he see me as a geophysicist. I kind of see myself as a tectonicist who applies geophysical data sets to understanding geological problems. That's how I view myself, and there's reasons for this. So when I'm a geologist, and I'm a geologist when I don't understand the math, that is often. And then when I don't know what the mineral is, which is every mineral, I'm a geophysicist. And so with that motto and that sort of view of myself in the world, I've kind of face planted my way through my career, and somehow no one's picked this up, which, well, people haven't been very kind to me and not said anything. There's two bits of defining feedback that I got really early on in my career, when I was an honours student, and then when I was in my second year of my PhD. One was given to me by Jim Carl, who said basically these exact words: "Shame you're doing structural geology, would have made a good geophysicist." That's what he said to me. And then Gordon Lister, who was a structural geologist, said to me, "It's a pity you like geophysics because you'd made a good structural geologist." So I did conjure up these images of myself being like the geological version of Dave Grohl, being excellent at drums and guitar, but I'm probably closer to Eddie the Eagle than that. So the first part of this talk, I have to give you some boring sort of background on aeromagnetic data. Some of the geophysicists will roll their eyes, some of the geologists will roll their eyes, but I do have to give it because if I don't contextualize it, it's very hard to understand what I'm going to talk about afterwards. The other thing that I want to start with this sort of background work is I want to contextualize some concepts in the things I think the geologists struggle the most with when they talk about geophysical data sets. And because I've kind of bridged the gap between the two disciplines in a sometimes unhealthy way, I do sense the geological community in particular, who get to access this data and talk about it a lot, really don't understand it as well as they should. And it leads to two things. It leads to an anxiety around actually doing something sensible with the data, and it also leads to difficulties in actually making sensible interpretations. And of course, the corollary to that is that the geophysical community often don't have the in-depth geological knowledge to pull out as much information of those data sets that otherwise can be pulled out of it. And usually that's often a lack of understanding of complex geological and geochemical processes that result in the signal in the data sets. And so I'm just going to highlight some of those points. I initially had 5 slides for this one point, and I decided to trim it down to 1 slide, which I had created earlier this year and forgotten about. So the Earth's magnetic field, which is essentially what we're measuring in aeromagnetic data, really has 3 bits. It has the main field, which is the field that's generated in the Earth's core due to a dynamo effect, which creates flux lines that make the magnet point north. That's all I'm going to say about that. And that changes over long timescales. So an extreme example of that is the polarity switches from the north to the south pole that we see in seafloor stripes that we've been able to map out in the top right corner there, left corner, right for you, left for me. Okay, I'm going to talk this way and it's got the same lefts and rights. Over the last 500 years, you can see the shifting of that field. So it changes over long time frames. And of course, we have to measure that and we have to understand that because we have to incorporate that into our understanding of that. We then have the external field, which is the field that's caused by forces outside of our Earth. And it's basically ionizing solar radiation from the sun. And it basically interacts with the Earth's magnetic field and creates things like solar winds and the auroras and stuff like that, which are spectacular. And last year we got a good long look at those in May, I think. And so they cause short-term variations in the field, and we have to account for those, and we basically can map those out and subtract them out of the data set. And the bit that we're really interested in is the Earth's secondary field, which is the signal from the rocks. So when rocks, like a magnet, are exposed to the Earth's primary magnetic field, what happens is they become induced and they create a secondary magnetic field. And that's the field that we're interested in because it's the field that tells us the story about the rock record. And so that's the one that we really need to focus on. Now, there's another component, which is the remnant magnetization, which is the ancient preserved bit. I'm not going to talk about that today, okay, because I got told there was a time limit. Okay, so aeromagnetic is basically magnetic data sets usually collected at a regional scale out of the back of a platform, often in an aeroplane, sometimes in a helicopter, and more commonly next to or below some sort of drone or UAV. Okay, and so the way the data is collected is we basically fly a survey grid, and I'm going to show you what that would look like in a minute. And we collect line data and then we process it to make it all leveled out so it's all kind of the same. And then what we do is we then grid that, and then once we grid it, you get an image that most of us get to see. And then we do funky things with that, often making stuff up, which is fine. I had a friend of mine who was a billionaire. That's not a gloat. He just made lots of money on the stock market running a mining company in Canada. And he said to me one day, he said, problem with undergraduates today is they're too scared to draw a line. And he said, all I want is an undergraduate to draw an effing line. I'd say I didn't swear. Good. On a map. And I said, why? And he goes, so I can make a decision. And that was really interesting and insightful to me. So we get these, after that gridding process, we get to see these spectacular images. So David Moore in the corner there, not in the corner in the middle. Put your hand up, Dave. Dave was when I was an intern at BHP, Dave was my boss. And Dave had me doing this really cool job where he had me on a big wall printing out individual aeromagnetic surveys and then getting the coordinates and sticking them up on a wall. And over several months, this image of Australia appeared, and on the fly, these guys were making terrain selections some of them were crazy decisions in hindsight, but that's okay, about where to go and explore based on this picture of the entire continent that was appearing in analog format. That was circa 1992. That's right, Dave, I think. And then 4 years later, the first generation of this digital version of this map. And this map we have the map that changed the world for the UK, which is the geological map. This is the map that changed Australia, 1994, 30 years ago. We're in the 8th edition now. It tells us what the continental architecture looks like. It's spectacular. You can see things like this. Who's a geologist who's never looked at mag? Tell me what you see there without reading the text. It's obvious. It's dikes. We see the patterns in the data and we know automatically what they are. There's a big fault in this one. We'll talk about that later. And here is this is up near Bendigo. In fact, where I point to township, where all the signal's a bit stippled, there is a whole bunch of dendritic patterns, you know, undercover, mapping out paleo channels for modern geographic context rather than an ancient geological record. So the data is amazing and it tells us lots of things. Anyway, we'll talk about all these things later. Okay, so we spent about $2 billion. I calculated that. I was making up some numbers as well. So it's plus or minus probably 1 billion. It's, you know, that's you know, that was conservative actually, because I didn't really count and couldn't count the industry expenditure on aeromagnetic data. It is probably the biggest data set expenditure in science in Australia. You know, to contextualize it, I don't think we've ever spent that much money on any other data set, and we don't use it enough. We have the best coverage on the planet. I've lots with my Indian colleagues. They have to either pay for their data or they have to buy the image, and then they sell, which usually got a contour on it, and then they have to digitize that, and then they grid it again. That's what they have. It's like butchering the data, and it's because they don't want to share it. Australia had a philosophy probably 20 years ago, and the government said, we're just going to share our data. It's amazing that we have that. The rest of the world looks at us with complete jealousy. So what are the problems? I think the problems with when we wrote the paper, we started to assess it, was we have issues communicating how to interpret it. And then when we start to interpret it, we have issues about that communication. I review papers all the time from all over the world about people having a crack at understanding aeromagnetic data sets. And the thing they don't all fail, almost 100% of the time, is they don't communicate what they're seeing. They talk about stuff, they don't describe it, and we end up with, I don't even know what these guys are talking about. Do you know what I mean? That's what it is. And the other thing is we don't, as a geological community, really understand what we do to the data to get it to that phase, and that's important. Okay, so data treatment is a mystery. Most geologists don't understand there's actually a relationship between the sensor height and the source of the magnetic response, which actually dictates what the signal will look like. We often have superposition of anomalies that we have to deal with, so multiple anomalies on top of each other with different sources. How do we filter it and image it, and why? And then how do we translate the rock properties, and it's really only one, which is magnetic minerals, into that image. And of those magnetic minerals, which is about 5 that really count, only one really counts, which is magnetite. And so this bit happens in the back room, in consulting offices, and with a handful of geophysicists that are out there doing this stuff. And then we just hand that over to these guys, and they go, tell us what it means. And that's the job of the geologist. And these guys struggle because they don't know this, and these guys struggle because they don't know that. And that's the truth. People will argue against me. Helen probably would, but that's okay. So Alan Aiken, another one of my PhD students, is a co-author on this. Alan kindly gave me this figure. It was the best figure I've ever seen to teach what the data does when you do it. So if you've got, we basically collect in each dot is a data point that we collected as lines equally spaced, and then we have tie lines. And then what happens is, if you collect data and the magnetic rock is between the data sets you collect, it doesn't pick it up. There's no way. You've actually got to put the sensor over that magnetic rock to get it to measure it. And if we put it over there, over the line, we will collect it. That's one part of the story. But then when you have multiple lines and multiple shapes, this is what happens. The greys are actually the true geometry of whatever rock we're looking at. And when we interpolate between those lines, so what we've got to do is we've got to take the data that's there, and we've got to guess what's between. That's the interpolation, that's the gridding process. And usually it's n divided by 3 or 4. If you're a risk taker, you make it 5. And you can see what it does. So if you've got a dike that's parallel with the flight line, it's going to make the dike wider because it's going to interpolate between nothing there and there. Okay? If you've got a little square, nothing picks up. If you've got 2 squares that hit the flight line, it wants to join them together. And so it ends up making something that looks like a linear feature. And so you have to have this sort of basic understanding of what's going on. And of course, they're individual things. And then if you've got dike arrays and you're collecting the data in the wrong direction, you're just going to get signals that are in the wrong direction. Anyway, so Alan gave me that. The terrain clearance as well. So I promised to give these talks without any maths. View slide number 1 for the reasons. But basically there's an inverse distance relationship between the magnetic source and the sensor distance. And so if you're a metre away from it, it's 1. If you're 4 metres away, you divide that by 16 times weaker. And so what you end up with is this source distance becomes really important. So here's a line data set collected at 20 metres, 30 metres, all the way up to 210 metres. And the information that you're collecting with that, for this one, all those superimposed anomalies are related to all those little blue dots. I made that up, by the way. And as you get further, the elevation or the distance between the source and the sensor, it's really picking up this one, and you might get a subtle signal in these things as well. So if you want more detail, you have to collect the data closer to the surface of the Earth. If you're interested in deep across the rocks, you can do that. Okay, and then we process it. And really, we process it for 2 reasons. The main one, and the one that I see a lot of mistakes in the literature from people having a crack at interpretation, is they don't reduce it to the pole. Okay, the reduction to the pole is a process whereby we take the Earth's field wherever it is on the planet and we recalculate it as if it's vertical. And the reason we do that is fundamentally the anomaly will change its shape to reflect the geometry of the body that's causing that anomaly. And so that you're able to interpret it. If you don't do that, it skewers the shape of the anomaly and you end up putting lines in the wrong spots. And of course, there's a consequence that if you're drilling, your anomaly is not in the right spot. So there's what happens sort of at a mid-latitude. There's a TMI, total magnetic intensity image, reduces the pole. You can see how the big blob has shifted its position and somewhat its shape. Okay. Don't worry about the linear histogram. What we've done here is we've upward continued it, which is like simulated the rocks as if it's being collected, the sensors, if it's collected from a greater elevation, and it gets rid of all the noisy bits, right, like this. And this is processing, which is a high pass field, a vertical derivative. I'm not going to talk you through the details, but it gets rid of the long wavelength and keeps the short wavelength component. And so whether you keep the long wavelength component or the short wavelength component is actually related to the problem you're trying to solve. So as the geos, you go, oh, I'm interested in this problem. That will dictate what you do with that data. Am I going too slow? Probably. Yeah, he's nodding. Bugger. Okay. The eye is an incredible thing. And so when we look at that imagery, geologists love looking at the colors. Oh my God, they're obsessed with it, right? It's crazy stuff, right? So this data and this data and this data is the same data and looks very different. And it's because your eyes are playing trick on your mouth. So you can see 1,000,000 of these colors. I'm red, green colorblind. I can see 1,000,000 minus 16. I only see 4 shades of red. This one is a grayscale. We see about 100 grayscale images. And so the imagery is 8-bit. So it's got 256 pixels. So you'll see all the color in this one. If you're not red, green colorblind, you see about 20 to 30 colors in this. And so what you'd have when you see a grayscale image is, because you don't see all the shades of gray, you see the contrast. So you see the boundaries and the anomalies really, really well. Okay, and so that's one of the advantages of doing interpretations using both types of data sets. don't worry about this, I've covered this off. That's how we basically do this. Of course, because we're obsessed with color, this is an image of exactly the same data set. And if you're obsessing about color, this image looks very different to this one. Okay, and all I've done to that one is I've stretched the color on how we turn the data into its 256 colors. The data's the same. You'll interpret it very differently if you're obsessing too much about the color in itself. It's really, really important message. And this is the grayscale one. And of course, when you look at this one, you see something really interesting in there, probably some sort of rift-related fault system. And in this grayscale image, there's not much contrast in that color. You can't see it at all. It's disappeared. So the data numbers, or each pixel value in that imagery, is the same for each one of them. So I think contours are kings. And when I say contours, the gradients in the data. And so I've just had this famous picture of mine that's from my lecture series in 2001. It's probably not that old, but anyway, but what you've got is a fold. And you can see that in this limb here, the gradients is much more gentle here than this side. It's telling you that body's dipping towards me. Same on this side. It's got a relatively shallow gradient. You can actually map plunges of folds out as well. There's a shallow, gentler gradient there and a steeper gradient there. You can use that to tell you qualitative geometrical information. Let's keep going. Okay, rock properties. I'm going too slow. Okay, the only thing we care about is ferromagnetic minerals, and that's that group up there. That's magnetite, maghemite, pyrrhotite, and basically the orbital domains are mainly aligned, and some of them are in the opposite direction. Whereas, for example, antiferro, sorry, what am I losing my mind here? This is supposed to be antiferromagnetism. They're all equally, roughly the same. So that's hematite, and so it doesn't have a signal in the magnetic data sets. And then you can have pure ferromagnetism, which is, you know, copper and in its purest form, and it's not magnetic as well. This is where we have the problems. This is the key figure for rock properties. It really says something really fundamental, which is you can measure the magnetic susceptibility of a rock and it's not diagnostic. So what I'm showing you here is two rock types, an acidic metamorphic granulite and a quartz porphyry igneous rock. And you can see that they have a bimodal distribution of magnetic susceptibility. Okay, and this data set was collected by Clark and colleagues way back in the early 1990s, and they measured thousands of rock types and mapped this out. And then if you just go up this vertical axis, and you can see everything that's got the same magnetic susceptibility, and it's the same thing. So magnetic susceptibility, the rock property that we measure, is not diagnostic of a particular rock type, which creates incredible ambiguity. Okay, so I'm going to really rush through this. So redox is king as well. And so you have that reaction at the top, which is basically in oxidizing conditions, you convert magnetite into hematite. Here's some other ways to do it. So you can do it by hydrothermal alteration, solid state, and some sort of mechanical breakdown in a shear-related system. If it's hematite, it'll have a low susceptibility, even though it's an iron oxide. And the reverse of that is if you have reducing conditions, you can take that oxidized version of hematite, so it's not oxidized, hematite, which is oxidized, and it reduces it down to magnetite. Same sort of reactions in reverse. And this is the mineral that is has a strong signal in magnetic imagery. And as a result of that, it is the thing or the mineral in the rock that actually gives you the signal. Okay, so now we're going to do the geology from geophysics bit. Thank you for dealing with a whole short course of 19 hours of lectures in 20 minutes. Don't say 30. You're going to say 30, aren't you? That's all right. Okay, I'm going to keep going. I'm going to start with basin systems, and then we're going to look at some metamorphic rocks, and then we're going to look at some igneous rocks, and then we're going to look at some structural geology. My comfort zone is the structural geology. I'm getting more obsessed with the igneous signal, and the one that's the most and least exciting is is the basins, even though that's where I cut my teeth as a young whippersnapper in the early 1990s. So this is a picture of Mount Isa. All this sort of signal that you see here is the basement rocks, right? And then what you see is this sharp gradients across here. I've got a point, I can use that. Look at that. Sharp gradients there, okay, where that signal is still visible, but it's much weaker. And what's happened there is that side of the block has been down thrown and the source sensor signal is increased. And so it actually weakens the signal, widens the wavelengths, and you get a visibility through transparent basins to see that. And so this is one way to map the fault. Two of the biggest basins in Australia, the Officer Basin and the Amadeus Basin. Here's the Musgrave Block. This is only basement rock sticking out of the ground because of the younger Peterman orogeny that happened in 50 million years. So it's a big transgressional deformation event, intraplate event. Popped all those basement rocks up, and to the sides sit these basins, and you can see those rocks are lying underneath those basins. You can also see the basin signal inside that, but what you typically see in these transparent basins is a weakening and blurring of the magnetic signal. Okay, and how blurry it gets is really dependent on the depth of that basin. Okay, and I don't find that particularly exciting, but it's actually quite important if you do want to map out basement architecture under that basement that you can't see. So, for example, horse and tilt block crests in extensional fault systems are types of things that you can see under those transparent basins that you can't see at the surface because it's covered with maybe a couple of kilometres of stratigraphy that's sitting over it. This is my favourite image on the planet. This is the Leichhardt River Fault Trough in Mount Isa. I did my PhD north of that, and we used to think we understood the geological record from the outcrop until Laurent, who's not here, he's out sailing today. I've got a gripe with him. He and I, when we were teaching this one day, we went, I don't think we got it right on the rocks. And what we learned was you can see this magnetic response here. This is a volcanic pile and it's folded. You can see it. Okay. And the story was that everything was deposited and then this fold formed. But actually what you can see from this is a big fold. And you can see these packages here that have no magnetic response inside it. They're tiny little half graben that are overprinting the limb of those folds. And the reason why there's no response there is because there's a package of sedimentary rocks that are sitting over it. They're deformed. They're just deformed. They're basins that were deposited after this folding event. You can still see little snippets and evidence of some of the features underneath that basin in that color image, but it's actually showing overprinting relationship between an inversion event and then the fold. We have this concept called magnetic stratigraphy, which is the layers in the rock that are magnetized. So it's not like a stratigraphy where you go, it's this formation and this formation all stacked above each other. It's actually the sequence of events. And so when you deform a basin and you've got magnetic horizons, the distribution of those magnetic horizons tell you something about that basin history. I really only want to show this one to highlight, for example, the salt dye piers in Central Australia, which are really only visible because that magnetic horizon has been upwelled and that dye pier has formed that circular structure there to create that. You can also map out that magnetic horizon. Here's one here. You can follow it around. Look how deformed and contorted it is. You lose it here. It's probably that. I don't know. Do you know what I mean? It's not my area of expertise. It's part of the world, but it is one way to do this. And this is the sort of thing that we would do to map out the architecture of the basin in the absence of outcrop, but also with a much simpler geometrical framework to interpret it. Okay, so it's really good for mapping out deformed patterns in deformed basins and correlating units in complex basins, salt dye piers, etc. We covered off. So Dave, thanks for these images. I like the one down in the bottom right the best. So I talked about this at the start. I'm not going to harp on it too long because for time, but we can see near surface features there. And that's because the magnetic minerals that form at the near surface are often, it's not magnetite, because magnetite typically would weather to hematite due to the interaction with an oxygenated atmosphere. But what you tend to have is a mineral called maghemite, and it often sits near the surface as magnetic, and it ends up being incorporated into paleo systems, whether that be drainage systems like you can see up here. Whoops, that's not what I want to do. Drainage systems up here, or aeolian systems and sand dune systems. They tend to form these strand lines. So here's some really obvious ones here up in Western Victoria. Okay, these ones are well inland. Okay, here's the Gippsland basement. That's the coastline, 90 miles beach. I'm from Gippsland, God's country. Don't argue with me. It's awesome. Don't. It's awesome. Bensdale is where I'm from, which is right about there. Second biggest silt jetty in the world. There's another fun geological fact about East Gippsland. Anyway, so you can see the strand lines there, and those strand lines are actually recording sea level changes. Amazing. Okay, so they give you proxies for really interesting. So you can see an old ancient channel in the basin, and then you can see messy signals related to basalts and stuff like that. I'll show you those in better detail somewhere else. Metamorphism. Now you're going to kill me because I'm going to dumb it down to the most basic level. When you take a hydrous mineral, let's call it clay, kaolinite. So that was, I've seen I could get maltobite, but anyway, so kaolinite. So it's got lots of water in it and it's iron. And so when you start to metamorphose it down into things in peelites, the reactions that typically happen is the breakdown of those minerals into simpler minerals like andalusite, sillimanite. But on that journey to breaking that mineral down, byproduct is often magnetite and water is exolved. So there's a bunch of reactions up there that I'm not going to talk to about how to produce magnetite in metamorphic rocks. They are favoured. So if you've got a rock that's iron poor, like a limestone or a quartzite, no matter what you do to it metamorphically, unless you add something to it, it's not going to make magnetite because iron is a fundamental ingredient for that making of that mineral. Okay, but if you've got lots of iron in it, biotite's a classic example, you will make, you can make the irons available for iron thing. But one of the interesting things is hydrosilicates, so shales and mudstones, tend to dehydrate and make magnetite. And that's because these minerals are the ones that break down, which is what I was talking about before. Silica undersaturated rocks favour magnetite formation. AL-rich silicates, muscovite, for example, reduce iron competition, and therefore the iron can be sequestered into magnetite rather than into the silicate mineral. Okay, partial melting tends to lower magnetisation. We don't really know why that is. I'm sure Mel does. And then, of course, if you start adding stuff to things like metasomatizing the rock, you can start to add or reduce magnetite depending on the oxidation state. Okay, my favourite bit of metamorphism, contact metamorphism. Serves two purposes. It's basically metamorphism on a small scale. And secondly, when you're trying to figure out where the edge of your granite is in magnetic data set, it often tells you where the edge is. And so here's an early study where they've kind of figured it out. Spear 1981, where they went and basically measured the minerals in and out, did the susceptibility and measured the magnetic field, and they went, the contact metamorphic aureole is a magnetic high. And then, of course, you go and look at all the data out there, and of course, most aureoles do, most granites or plutons with an aureole have this tiny little rim that around it. Sometimes they're bigger rims, like these frog's eyes here in central Gawler Craton. They're quite large aureoles, and sometimes the aureole is actually buried beneath the granite itself. The pluton's in place and the aureole's below, and you can see here the edge of this granite here. You can make it out in the high frequency response there, but this big low here is actually the underbelly aureole of that. There is a relationship between the scale of the aureole and the and the width in the magnetic response. So that's the scale, sorry, and the cooling temperature. So the slower it cools, the wider the metamorphic aureole is. And if it's shallow level plutonism, it typically tends to be quite a narrow thing because the rocks cool much faster. Okay. Now I'm going to go and freak everyone out because, and I hope you've all noticed that most of the examples are from Victoria. In the paper it is as well. This one's an example from South Australia. We won't hold that against the image, shall we? Okay. So, oh my, this has been recorded, isn't it? Okay. So there's basically we can classify granites multiple ways. One common classification is the magnetite and ilmenite series. And that was kind of done roughly in parallel with Chaplin White's I-type and S-type granites. They pretty much say the same thing. For mag interpretations, I just swap between the two, it doesn't matter. So magnetite series typically form in oxidizing conditions, so there's a higher oxygen efficacy, so the flux of oxygen is higher, and these typically contain magnetite, and they have strong magnetic signals. And so look at these granites here. This is one big nested pluton here, and there's lots of little granites. You can see this, that's a granite there. This blurry bit, it means it's at depth somewhere. We'll look at this one a bit later on. So lots of magnetite series granites here. They are all I-type granites. They're all sitting out there, Ordovician age at the edge of Victoria and South Australia. And then you have the reduced granites, which are ilmenite series. So rather than magnetite, they produce ilmenite, and they tend to be weak and they tend to correlate generally with S-type granites. And this bad boy here, which is pretty non-magnetic, very transparent, is a S-type granite. Okay, very different response to the magnetite series granite. And so what you see here is you can pick the edges basically because it's truncating and terminating linear features that probably represent stratigraphy. Okay. Of course, there are lots of other processes that impact this: oxygen, silica contact, how the cooling rate is. So when you cool a granite and it's got magnetite in it, the crystal size of the magnetite changes. And so the crystal size actually can impart a significant response in the magnetic data set. Okay, so one of the interesting things about granites in the magnetite series is you often see these outer rims that are magnetic. Okay, and then you have these middle bits that are non-magnetic. This is up in northern Victoria, and here's one from Mount Isa. This is the Wimberoo granite. Put this one in for you, Mel. So, and you can see lots of magnetic response, now low in the middle. Here's another sort of different part of that granite, and you get this low in the middle. And so what's happening here is under oxidizing conditions, the magnetite will crystallate out early as part of the fractionation process. And so you get the outer rim of that's magnetic, and then when that reaction is no longer available, you start to get the iron starting to be partitioned into silicates. And then when all that fractionation happens, and in the middle of the granite, you basically have no iron available for anything. So you end up with minerals that don't have much iron in them. So, and you get this, which is kind of cool. So this is not just related to the oxygenic acid in the cooling history. It's actually part of the fractionation process of granites. And I think, when you walk over those granites, I'm pretending they're actually outcrop. I think it'd be really subtle to pick the difference between that bit there and that bit there based on the bulk mineralogy. Do you know what I mean? By just looking at it and going, look, there's the feldspar, there's the hornblende, there's the whatever part of it. But the magnetic data sets tell you something about the internal structure and the fractionation history. So what if you consider the next phase of complexity, like a sill, which has multiple pulses of magnetism during its emplacement, and you see the patterns again. So I've just drawn this on the PowerPoint, so it's not really high tech. But what you can see is a rim, a low zone. Here's a low zone there, and another rim. Here's another demag zone, so where the iron's not being part of the reaction to make magnetite, and then you get the magnetite rim there, another low zone, another one. And so this is telling you about the pulsing of that granite in its formation. Okay, now I'm really going to mess with your minds. Okay, The structural geologist in me wants to say this is a shear zone. It just does. Okay. Anyway, so much smarter individuals than myself, Sandy Cruden and his team of PhDs in recent years have been doing lots of experiment. And that's not working. They're going to play. Mark, can I get you to play that? Thank you. So two PhD students, Jonas Copping and Uchi Ruchiji, I can't even say his last name, are both PhD students. Ruchi was doing analog experiments and Jonas was doing 3D seismic interpretations of sill geometries. And what they figured out was that there's some patterns in sill placement that create particular geometries. So this one really talked about the placement mechanism and the geometries that are created, and they classified them into type 1, 2, and 3. It's kind of, you can see type 1 is fingers, type 2 is these sort of long linear ones like this, and then type 3 are these lobes with big frontal flat zones there. Okay, really interesting. Then you look at this mag image and you go, wow, I can see some really interesting things in this data set that look like some of these crazy features. Mark, I'm going to get you to keep doing the repeat thing because I'm a Gumby at PowerPoint. I couldn't set it up to be on repeat. So look at these things. Fingers like this coming out of those granites there. Here's another one. Okay, so at the front of these sill lobes, you're getting these magma fingers coming out, imaged in the data set, telling you that we're right at the front of whatever lobe that was forming. And it's often the last phase of the magma emplacement. This one's even more interesting, right? I'm not going to talk to all of them, right? But I'm going to talk to this one, right? So you've got this feature here that you can map out there. It seems to be overprinting something else there. This is this magnetite rim there. Okay, you've got a propagation this way and a propagation this way, which is pretty common in sill emplacement. And then this outer rim becomes solid. Okay, and then this next phase of magmatism, which is now more fractionated, without the magnetite forming in it, has started to propagate into that way. And then of course you've got these spectacular ones here where there's 3 lobes that are just spilling out from that. So you don't need to be a structural geologist to interpret this. It's actually all about igneous emplacement. If you look at this image here, you can see this. I'm going to get you to play it one more time, just so to conceptualize this. Okay, if you watch this play out, this is an analog experiment with 2 fluids, basically designed to mimic this. This is the propagation. There's a needle here, and this is the propagation of those sills. And you can see the fingers forming. You can see those frontal lobes, and as this solidifies behind it, the next lobe comes out, and it keeps propagating out and out. And I think we've been misinterpreting many of our igneous plutons because we haven't understood the process by which sills have been placed. Now, this sill here that Jonas was working on is a 2-kilometre size sill. And my English skills are poor. Anyway, this scale, this is 50 kilometres. This is a 100-kilometre long sill system. It's massive. It could, I'd be interested to see, what would be larger from a granite perspective on the planet from that. So Mount Henry, which is the big laccolith, is about half the size of this. That's in Utah, for those that like their igneous intrusion methods. Yep, I'm going to fast. So dikes, I'm not going to talk about dikes at all. Chris Wilson's paper showing how different dikes work. When you look at the details, all the features are there. The step overs, the echelon arrays, the braided dikes, etc. They can all be imaged at the next scale up. This is the scale of meters. There's 10-meter scale bar there. That is the scale of 100 kilometers. Everything is scale invariant in these data sets. You can see that. 10 minutes. Wow. Okay. Volcanic rocks. Okay. Typically have a high frequency stippled response. Sometimes you get the effects of sheets where you see the longer wavelength there as well, but often you get this stippled texture, and then you get these dendritic patterns which record ancient paleo channels related to that. This is Western Victoria, by the way, new volcanic province, underrated part of the world in my mind. It's awesome. Okay, you can actually see the individual Mars here as well, related in the data set. I'm not going to talk too much about that. I'm going to talk a little bit about this one. This is the new, this is the Gawler Range Volcanics, so really famous because it's associated temporally with the Olympic Dam deposit. It's also the most unusual volcanic province probably on the planet. It is felsic, it is rhyolites, and it has flow fronts on the order of 50 to 100 kilometres, which means the rheology for that rhyolite is not right. Okay, and it's got such high halogen contents in it that it actually is behaving, when we do the calculation, it looks like it flows like a basalt. Okay, everyone used to think it was enigma, and then our volcanologist went out there and went, hang on a second, it's not. And so, but the cool thing about this is you can see the frontal lobes on those flow fronts. You can see them there. They wrap around this province. Some of them overlap a little bit. It's like this one goes like this, and then this one is a big one, another big one there. And actually, when you draw them tangentially, they all kind of land there. It kind of tells us where the eruption point is. Those rocks are 1.6 billion years old, by the way. So yeah, so we can do stuff like that with that data set. Ring complexes. So I'm just going to highlight that. The ring complex here is this magnetic high here. It's a fault zone, and this is a collapsed caldera. I'm not going to talk too much because I want to get some faults going on. Faults are really obvious. Most people who are not skilled at mag interpretation can interpret the easy faults, and those easy faults are these ones, the ones that are kind of at a high angle to the overall grain. Okay, we know this because when we do third-year teaching exercises, the students always pick those faults out first. That's the litmus test. No experience, I can see that fault. Other faults have strong signals actually in the fault zone itself. These faults don't really have a signal, they're just mag low zones. This one does have a strong signal. This is the Mundraville fault. It's probably the biggest fault in the country. It's not really exposed. It can be traced out into Antarctica. That's about 20 kilometres wide, shear zone. And you can see the magnetic units here wrapping up, giving you the kinematic story. And so we've kind of classified these as high angle faults and these ones as kind of low angle faults. We'll have a look at these ones. This is the Kalanjala myelinite zone. Pretty spectacular outcropping. If you go right into the ultramyelinite bit and you stick a magnetic susceptibility meter, it goes off the tree. So there's something going on there about magnetite production. And if you go and look at this shear zone, which goes all the way around here like this, and then you can see some really funky folding down in there, you can see that these anomalies here are truncated against that, like this, at a really low angle. And most people don't interpret that. But they're really critical structures. And I've picked the most obvious structure on the planet to illustrate that. But when you start to see those low angle faults, you start to see other patterns. So here is, this bit here is this bit here, and that bit there is this bit here. What you see in this data set is a big magnetic horizon, and then suddenly it splits into three, and then it reappears out that way. Who wants to have a guess at what that means as a structural geologist? Don't be shy. So it could be splays. Yeah, so that's one interpretation. The other way is the duplexing. So you're doing that in a duplex system, and then you folded it over on its side, and you're seeing it in essentially in cross section. Don't know the answer because I've never been there. I'm just guessing. But illustrating it. Here's one of my favourite images. This is in the Musgrave Block. Here is a series of strike slip faults. You can tell they're strike slipped because these magnetic horizons are wrapping into them. Gives you the kinematic history. And under those kinematic regimes, the step over from that in the termination of that fault to that fault will predict that you get a pull apart basin there. And then when you look at the magnetic signal, you get this sort of blurring out of the magnetic response. And that is those rocks that are giving that really stippled texture buried underneath a relatively thick pile of sediments that are sitting underneath that. Kind of cool. Folds, I'm kind of a bit obsessed with them. These are my favorite folds in magnetic data sets. We basically can assess whether they're anticlines or synclines based on the plunge and you've got to use the gradients to do that. So you can't tell whether that's an anticline or a syncline by just guessing it. And you've got to actually go and get into the hinge and figure out which way the shallowest gradient is. Yeah, really effective geophysics for picking up upright folds or inclined folds. As soon as they become recumbent, terrible. Okay, so anything that's got a flat axial plane, we don't really do that well. How long have I got? Fold interference patterns. Actually, the importance of fold interference patterns is most of us, when you're a structural geologist, can see them. Okay, they're kind of funky and they're really interesting. Took me a while to get my head around that business of figuring it out. But this is a Davenport province, and this is type 1 interference. So there's a shortening this way and a shortening at right angles like that, and you create eggshell or dome and basin type thing. So what the second deformation event does was make the plunges of the other folds in different directions, and so you end up with these nice sort of domal patterns and these simformal patterns in there. This is probably the most spectacular example of this in the world. Okay, and you can read information about the geometry, but you can also tell stuff about the tectonics. Sometimes it's hard to get the overprinting because you don't know whether this one was first or this one, and then you have to find alternative information about that. Here's some work from Sheree Armisted's honours work, where she basically identified this in the Alleri domain as a type 2 interference. So this is a type 2 interference is a recumbent fold with a horizontal plane, and then you fold it over like that. And then when you plunge it one way or the other, it turns out to be look like a Christmas tree or a mushroom or something like that. And so that's that's my son coming home. That's the mushroom tree. The Christmas tree shape. This is the F2 fold locally, and then it's been folded by an F3 fold. Interestingly, when we looked at the geometry of this, what it told us was the recumbent fold transport direction was to the south, which is exactly the opposite to the way that everyone else was interpreting those recumbent folds in the Broken Hill domain. And the only way that you can make them go south was in an extensional regime. You had to flip the tectonics on its side to understand what it really meant. This is up near the Eyre Peninsula. This is this structure here is the Kalanjala shear zone, and this is a type 3 fold interference pattern, which is when you have snakes and then you upright fold them and you end up with these crazy fold interference patterns. Okay, let's keep going. Overprinting is done best with igneous rocks. Okay, really obvious examples. This is an I-type granite in eastern Australia. Here's another example. You can see the layering of this pluton, but you can see the fault cutting through it and offsetting it. And then you can see overprinting in this one of this granite, overprinting the folds. Here's an even more interesting one. Here's the folds overprinted by the granite, and then you've got some sort of structure there that's overprinting that granite, making this blurry, which means it's been downthrown relative to that. So you can piece together geological histories by just applying first-year principles that we all got taught by Vic Wall in 1989 about how to interpret things. And if you just apply those same principles to data sets, you can get something out of it. Okay, so kinematics, Mel and I would look at this stuff and try and infer the movement history of rocks. The interesting thing about this is we look at those rocks at those scales, millimeters, microscales, really interesting things, but you can see similar patterns in a much larger scale. Okay, so here's the elder shear to shear zone there. Here are these granites. It's basically a wide shear zone with granites in it, and the geometries that are produced are not dissimilar there to the geometries that are produced there. The processes are different. So what we're looking at, for example, in an SC fabric, so here's two shear zones there running parallel, and you can see these sorts of geometries that look like an SC. You can see a really good example here to what looks like a C plane. Here's an S plane there. Okay, in microstructure, SC fabrics are a recrystallization process. Okay, this is not being produced by recrystallization. It's just actually existing geometries that have been changed, but you can interpret it in the same way. So you can get the large scale movement picture of this. This rotation of this shear zone into this shear zone, that's about 30 kilometers of rotation of a shear zone, which means it's probably had about 300 kilometers of movement on it to do that. Okay, here's a microfiche, and there's structures that look like broader microfiche, and some of the other examples, not this one, you can actually see those exact same sort of fracture patterns as those dislocations and those microfiche happen. So we're seeing things happening at a crustal scale that are also happening at local scale. Finally, the 3D geometry. Just looking at data sets that won't tell you about the three-dimensional geometry because of all their factors like the rock properties and the source sensor distance. You actually have to do qualitative approaches to that. Okay, I'm a Ford modeler. That's my bread and butter. People think it's easy. I think it's hard. Maybe that's telling me something. We often do inverse models, and sometimes if you want to get really funky, this is Cherie's paper. You can do modeling that's historical. So use something like NODI, give it a history, calculate its response, and see you go. There's two approaches. This is the approach that I don't like, which is a reductionist approach. Let's just fit the data to the most simple geometry. Kind of works okay when you just want to get something a bit loose. Yeah, mate. I've got 3 more slides. So I actually see Ford modeling as constructing geological cross-sections constrained by geology, geophysics, right? That's what I said. And then when we do constrained inversions, and we can do unconstrained inversions, which I don't like because that's a data set and we did an unconstrained inversion that did that. But actually for the same data set, the constrained inversion, which involved some modeling, some 3D model building, and then the inversions create something that actually looks like the geology. Okay, so we would avoid that at all costs. Here's a workflow. Start with an interpretation. I thought I'd give one so that I can actually do it. Start with interpretation. We often do the Ford modeling. Then we put it into 3D modeling package, depending on which one you want to do. We have a model. Then we do the inverse modeling and we flip it around doing rock properties and geometries. And then we finally get a 3D model. Okay, and then the decision about what we do here is actually based on the problem you want to resolve. So there's no cookie cutting, let's do this. You've got to figure out what the problem is, and then you've got to figure out which method you want to use. Okay, last 2 slides. So what's next? Machine learning is the thing that I'm getting most into for a bunch of reasons. Partially serendipitously, Ange Rodriguez is a machine learner in our group, and she replaces me in the classroom. And I said, oh, what do you want to do? She goes, oh, I need to collaborate with someone. I said, okay, let's do something with machine learning and geophysics. So we did some stuff. Josh is in the room. He's my newest PhD student, just there. He's done some work on this. And so I feel like the future of our analysis for the moment is in machine learning. Here's an example of statistical method. I'm not going to talk to that, which is basically linear analysis from another PhD student. Paper came out last year by Chibuzzo. He basically did an Euler deconvolution, which is a calculation of the depth of the magnetic source. And then he was able to cluster those depths. And then scarily, without going into the details, after processing those clusters, he was able to create cluster boundary structures that look like faults. And then they look very much like the seismic line. Many millions of dollars, 1/3 of a PhD scholarship. Scary. Sorry, that was a joke I just literally made up. So, and so I haven't put Josh's work in there. I don't think I have. No, I haven't. I actually did Aaron's because Josh gets a Guernsey in my ASCG grant. It's getting submitted tomorrow. So basically a bunch of input data. In here we just used mag, gravity, and radiometrics. And what we wanted to test in this project was, can we do unsupervised clustering, machine learning clustering, and see if it would predict the I-type and the S-type in the Eastern Tasmanites, and scarily so, it did. Guess why? Because the magnetite series are the I-types, and so the clustering was able to pick that, so we weighted that. And then the S-types, which have a poor magnetic response, were able to pick it. We knew what we were doing because there's a chemistry that's attached to the classification of the granites, but also in the geophysics. Okay, last slide, promise. Okay, so this is what we used to do. We used to bump stuff when I was born. Okay, when I got to Dave, we were in the transition from contours to imagery. And then kind of sort of at the late 1990s, we started to go, let's do it all digitally, and we started doing interpretations, et cetera, in GIS, right? That's what we did, okay? Forward modeling's been around for a long time. Started off pretty basic, the reductionist approach, got more complicated as geologists had a crack at it, like myself. So an increasing level of complexity. And I remember in 2002, BHP did a tour around all the universities and said, inverse modelling is the future. That's what they said. I forget who the person was. And I remember looking at Laurent Ollier and going, this is bullshit. Actually, did I swear? Sorry. Anyway, 2 years later, we're all doing inverse modelling and trying to get this going. And then we go from unconstrained to constrained. And now we're looking at these statistical methods. And the difference is because all the interpretation feeds into the outcome, which is the 3D model. That's what happens here. You basically go through a workflow that lands there. Now we're doing statistical methods and machine learning methods, and they are part of the workflow that actually constrains the interpretation. Okay, so we've flipped it around on our head. So the thing that most of us are getting into now is actually not things to make the 3D model, it's things to make our interpretation better. And I'm going to leave you with that point to finish off with. Thanks.